Sometimes we can use Taylor series to help us find derivatives as well. Let's say we wanted to find the derivative of arctangent of x and we didn't already know the answer. Could we use power series or Taylor series to help us figure that out? Well, we know that f of x equal to arctan of x is equal to the power series x minus x cubed over 3 plus x to the 5th over 5 minus dot dot dot, which is the sum, k goes from 0 to infinity, of negative 1 to the k, x to the 2k plus 1, all over 2k plus 1. And that this is valid if the absolute value of x is less than or equal to 1. So x being greater than or equal to negative 1 and less than or equal to 1. Well now, if we want to take the derivative, f prime of x is going to be the derivative of arctan, which is what we want, but it's also going to be the derivative of this power series. X minus x cubed over 3 plus x to the 5th over 5 minus dot dot dot. So that means that it should equal 1 minus x squared plus x to the 4th minus x to the 6th plus dot dot dot. But what power series is this? Well, notice the pattern. This is 1 minus x squared plus x squared squared minus x squared cubed plus dot dot dot. So we're replacing x with x squared, and then we're getting powers increasing by 1. And we're alternating signs. So this is a geometric series. Let's rewrite it one more time. 1 minus negative x squared plus negative x squared squared plus negative x squared cubed plus, notice now that we get our alternating signs because that negative comes out whenever that's to an odd power. So now we can see our power series is just geometric. It's multiplying by negative x squared each time. So this is going to be equal to 1 over 1 minus negative x squared, which is 1 over 1 plus x squared, which is what we expected, right? That's the derivative of arctan. But you could see how you could use a similar technique to find derivatives of things you didn't already know. Now let's look at another example. Consider the differential equation at y prime of t minus 3y of t equals negative 2, and we know that y of 0 is 5. And we're going to use Taylor series to try to solve this differential equation. This is one of the most powerful applications of Taylor series. This is going to be a really simple example, but you can take, courses and courses on just solving differential equations, and because they come up quite a bit in applications. So here we're going to assume there is a solution, y of t, and we're going to assume it's a Taylor series centered at 0. So it has, this form of a Taylor series, and we want to find the coefficients. So do we have enough information to do that? Well, what do we know? We know y of 0, and since the power series is going to be c0 plus c1t plus c2t squared plus c3t cubed plus dot dot dot. We know if we plug 0 into that, the only thing left is going to be that c0. Every other term is going to be 0. So we should be able to say that 5 is equal to y of 0, which is equal to c of 0 plus a whole bunch of zeros. So c0 has to be 5. Okay, well that's great, but that seemed like a trick. Can I say anything about any of the other coefficients? Well, remember what we do know. We know something about the derivative. We know that y prime of t minus 3y of t is equal to negative 2. So how can we use that? Well, that means if we plug 0 into this equation, we get y prime of 0 minus 3 times y of 0 should be negative 2, but we know y of 0, so y prime of 0 minus 3 times 5 should be negative 2. So y prime of 0 is going to equal, we're going to add 15 to the other side, so 13. Okay, so now we know y prime of 0 is 13. But just like when we knew that y of 0 is 5, this is going to allow us to find a coefficient. Now we can take the derivative, y prime of 0, of our power series. Maybe let's write that out one more time. So we can look at y of t equals c0 plus c1t plus c2t squared plus c3t cubed plus dot dot dot. Now we can take that derivative. Y prime of t is going to be, c0 is going to be 0 plus c1 plus 2c2 t plus 3c3 t squared plus dot dot dot. And so we know that y prime of 0 is 13, and also that it is 0 plus c1 plus a whole bunch of zeros. So c1 has to be 13. Well, what about the rest of them? What about the second derivative, the third derivative, the fourth derivative? Well, we know that y prime of t minus 3y of t is equal to negative 2. So we know, taking the derivative of both sides, that y double prime of t minus 3y prime of t is equal to 0. And that tells us that y double prime of t equals 3y prime of t, which means that y double prime of 0 is 3 times y prime of 0, which is 3 times 13. And notice that if we keep differentiating this expression right here, we're going to get, y triple prime of t is equal to 3y double prime of t, y to the fourth power derivative of t is going to be 3 times y to the third derivative of t, and we could keep doing this forever, right? So we found a pattern. We found that every time we take a derivative, we multiply the answer by 3. So in general, we have that the kth derivative of y at 0 is going to be 3 times the k minus 1th derivative, which means it's going to be 3 to the k minus 1 times 13. So we know that for all k, well, k big, k equaling 1, 2, 3, etc., that we found a pattern. We have ck equaling the yth derivative at 0 over k factorial is going to be 3 to the k minus 1 times 13 over k factorial. So we have our solution. It's y of t equals 5 plus, remember 5 was the c0 term, plus 13t plus 3 times 13 over 2 factorial t squared plus 3 squared times 13 over 3 factorial t cubed plus dot 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 dot. But what function is this? Well, let's see if we can recognize it. Notice that, once we start looking at this 2 factorial term and this 3 factorial term, we're looking at powers of 3 on top and factorials on the bottom. So what do we know that might look something like that? Well, we know that e has power of x on top over a factorial on the bottom. So what about if we wanted power of the 3 in there too? What about e to the 3t? What would that be? Well, that would be 1 plus 3t plus 3t squared over 2 factorial plus 3t cubed over 3 factorial plus 3t to the 4th over 4 factorial plus dot 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 dot. So the question is, how is that like what we had before? Well, what's different? Well, there seems to be lots of 13, so let's try multiplying everything through by 13 and then see if it starts to look closer. So now we have 13 plus 3 times 13t plus 13 times 3t squared over 2 factorial plus 13 times 3t cubed over 3 factorial plus 13 times 3t to the 4th over 4 factorial plus dot 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 dot. Okay. Well, okay. Now let's compare. The first few terms, notice, are kind of off. We'll have to fix those later. Can we look for a pattern in these higher terms? All right, so in the sequence we want, we would have 3 times 13 over 2 factorial. We have the over 2 factorial, we have the 13, and we have a 3 squared t squared. We want just a 3 t squared. In this one, we would like a 3 squared 13 over 3 factorial. We have the 3 factorial, we have the 13, but we have a 3 cubed t cubed. So we have one more power of 3 than we want in these. So let's take everything in this e expression that we're working with here and divide it by 3. So 13 over 3 e to the 3t is going to be 13 thirds plus 13t plus 13 times 3 over 2 factorial t plus 13 times 3 squared over 3 factorial t, wait, this one's t squared, t cubed. And if we continue this pattern, we would have the next term would look like 13 times 3 cubed over 4 factorial to the 4th, etc. Okay, we're getting closer. Now all the terms after the squared match the series that we want. See that? So we need to figure out how to make the first couple terms match. Well, these first couple terms are just, we can just add stuff to make it match. So we have 13 over 3, and we would like to make that 5. So what's 5 minus 13 over 3? Well, there's a 2/3 difference there. So let's take our y function that we want now, and it was 5 plus, well, look at that, even the 13t is matching. So 5 plus 13t plus all this other stuff. And let's compare it with this series. Well, if we take our y of t series and we rewrite it as 13 thirds plus 2 thirds, adding those together, we'd get 5, right? 15 thirds. Plus 13t plus all the rest of this. Well, actually here, let's change the order of these two and make it 2 thirds plus 13 thirds. All of this part, we know what that is. That's the power series we kind of finagled there, 13 thirds e to the 3t. And so we get that y of t is equal to 2 thirds plus 13 thirds e to the 3t. So we were able to recognize that power series as similar enough to one that we knew that we could manipulate it until it actually matched. Now you could check this answer by actually taking its derivative and plugging it back into the differential equation and seeing that both sides of that differential equation actually end up being equal. Alright, now here's one of my favorite applications of Taylor series. We're going to integrate e to the negative x squared. And I want you to think about it for a minute. None of the techniques we know so far will allow us to integrate e to the negative x squared. But if we rewrite e to the negative x squared as a power series, then we know how to integrate it, right? Because you can just integrate power series term by term. So let's rewrite it. We know that e to the x is the power series k goes from 0 to infinity of x to the k over k factorial. So e to the negative x squared is going to be the power series k goes from 0 to infinity of negative x squared to the k over k factorial, which is the power series k goes from 0 to infinity of negative 1 to the k, x to the 2k over k factorial. And now, if we want to integrate it, the integral of e to the negative x squared is the same as the integral of the power series, which is the same as the power series of the integral. This was a big theorem that we had. But remember now, the integral only cares about x. It doesn't care about those k's. So this is just the sum k goes from 0 to infinity of, we keep our negative 1 to the k, we keep our k factorial, and we just take the integral of x to the 2k to get x to the 2k plus 1 over 2k plus 1. Well, that's a power series. And we can add a constant to that, right? We integrated, so we should add plus c. This is a power series. And it's a function then. So it's an answer to our integral. Now, we don't actually know a closed way of writing this. This is an example of a new function that you get from power series that you didn't have before. The antiderivative of e to the negative x squared, the easiest way to write it is as a power series. All right, now this problem asks us to approximate the integral of e to the negative x squared from 0 to 1 with an error of less than 10 to the negative sixth. Now this makes sense because we have the antiderivative of e to the negative x squared as a Taylor series, and we know how to approximate Taylor series to within a certain accuracy. So let's remember what that Taylor series was. It was the sum, k goes from 0 to infinity, of negative 1 to the k times x to the 2k plus 1 divided by k factorial times 2k plus 1. So that antiderivative of e to the negative x squared was equal to this plus c. So if I want to do the definite integral from 0 to 1 of e to the negative x squared dx, well, that's going to be the indefinite integral, the antiderivative here, evaluated from 0 to 1. So we're just going to plug in 0 and 1 and subtract. Well, this is the sum, k goes from 0 to infinity, of negative 1 to the k, 1 to the 2k plus 1, minus the sum, k goes from 0 to infinity, of negative 1 to the k, 0 to the 2k plus 1, over k factorial, 2k plus 1. Now notice that in this term, every single term is multiplied by 0. Even when k is 0, we have 0 to the first power. So every single term in here is equal to 0. And the sum of 0, 0, 0, 0, 0, 0, 0 is going to be 0. So we're left with just figuring out what this sum is. Well, note that, no matter what power we raise 1 to, we get 1. This sum just becomes the sum, k goes from 0 to infinity, negative 1 to the k, over k factorial 2k plus 1. And we want to figure out, what that number is to within 10 to the negative sixth. Before we can even ask that question, we should ask, well, does this series, that's what we have now, right? Does this series actually converge at all? Well, we need to use one of our convergence tests to answer that question. Let's look at the alternating series test, because this is an alternating series. It has a negative 1 to the k on top. K factorial is always positive, so it's 2k plus 1. So that would give us an a sub k equaling 1 over k factorial, 2k plus 1. So what do we need for this? We need non-increasing and going to 0. So convince yourself that a sub k plus 1 is always going to be smaller than a sub k by looking at the terms. It would be 1 over k plus 1 factorial times 2k plus 1 plus 1. And we're comparing that to 1 over k factorial, 2k plus 1. Well, k plus 1 factorial is bigger than k factorial, so that makes this smaller. And 2k plus 1 is bigger than 2k plus 1, so we also added a bigger thing to the bottom for that term, so that one also made the k plus 1 term smaller. So yeah, it is non-increasing, and if we look at the limit as k goes to infinity of the a sub k's, we can see the bottom goes to infinity, top is constant, so this is 0. So it converges by the alternating series test. And in fact, what's more than that, remember we have a remainder bound for the alternating series. Remember that we know then that the remainder, r sub n, is always less than or equal to a sub n plus 1, which is, in this case, we figured this out already, we called it k, but let's just call this one k too. So the remainder r sub k is less than or equal to a sub k plus 1, which is k plus 1. 1 over k plus 1 factorial times 2 times k plus 1 plus 1. So now, if we want an error of no greater than 10 to the negative sixth, we want to make this number less than 10 to the negative 6th? Since we know our error is less than that. Well, again, there's not a really great way to solve this, but just try to plug in a couple different numbers. And it happens to be if we plug in 8 for k, we would get 1 over 9 factorial times 19. And that's approximately 1.45 times 10 to the negative 7th. So that's less than 10 to the negative 6th. So we know if n is at least 8. But that's better than 10 to the negative 6th. We know if k is at least 8, then the error is less than 1.45 times 10 to the negative 7th, so it's less than 10 to the negative 6th. So we can say that the integral we were trying to estimate, and this is a definite integral, the answer should be a number, and it might be a number we actually needed to know for some reason, is approximately the first 8 terms here. So that would be 1 minus a third plus 1 over 5 times 2 factorial minus 1 over 7 times 3 factorial plus 1 over 9 times 4 factorial minus 1 over 11 times 5 factorial plus 1 over 13 times 6 factorial minus, let's see if we can squeeze this in here, 1 over 15 times 7 factorial plus 1 over 17 times 8 factorial. And that number ends up being approximately 0.7468242657. So we were able to find a numerical answer to this integral, even though we couldn't find an antiderivative except for as a power series.